So we're now at section 8.5. And the concept of power. So long story short, power is the rate at which you use energy, the rate at which you use work, right? So power is work divided by a time interval. I just say time for short, delta T. How much power are you going to use in your engine? How much power does it take for you to lift a ball in the air? Because you can see a pattern. Hopefully you start seeing a pattern. Like you can talk about positions, you can talk about changing little things, changing velocity, changing position, changing work, changing energy, changing kinetic energy, changing potential energy. But then it just, out of the sake of curiosity, we come to figure out, we come to ask, well, what happens when we introduce time? If I change something with respect to time, what happens then? What new quantity can I talk about? So we've had this concept of work, changing kinetic energy, changing potential energy. And now we take those energies with respect to time, and we have the concept of power. Power is the rate of change of work. Velocity is the rate of change of position. Acceleration is the rate of change of velocity. Rates of change, you'll see that in calculus. If you haven't already, if you're taking it. Very important because time is, on the esoteric level, it permeates, moves through everything. I have a hypothesis on time. It's the flow of gravity. Nothing more esoteric than, say, the concept of general relativity, but I'm in the concept of developing just my own thoughts about time. Many thoughts about time in terms of the general relativistic framework, and take that and say, hey, can we make it easier? All right. Time is everywhere. It involves everything. Through time, we change X, Y, or Z. And this concept here, power, the rate of change of work. Or short form, work divided by delta T. Can I get one volunteer to give me a different way of saying this equation? Basically, what's another term for work? Work is something we've seen already. I want to rewrite this. I want to rewrite this equation. Instead of saying W, can I say something else up the numerator?
Delta kinetic energy.
Yeah, change in kinetic energy. We know from the work kinetic energy theorem, work is equal to change in kinetic energy and also change in potential. So depending on what you have, and we're going to see a third way, depending on what you have, velocity, I can change in velocity, that is, I can change the numerator to delta KE over delta T, because that's work, right? And likewise, too, work is also equal to change in potential energy. Let me do something first here. Power, work divided by time, this is W over T, and short order, work over delta T. Thank you, Sen. Yes, I can say this as well. Change in kinetic energy over delta T. It's the same thing, because work is the change in kinetic energy. And also, work is a change in potential energy. Notice I don't have the negative, because when we talk about time, power in this context, or talk about power, the context is going to give me always a positive number. So this is kind of like absolute value, if you will. It's how much am I going to use, right? So if my engine gives me a certain amount of power, we're always going to look at power in terms of a positive number. Questions? Seems fair. Take this one particle, we change its kinetic energy, and we get work, and change the position of that particle, we get change in potential energy. Notably gravitational. We could also do spring, but I'm just going to say delta PE because it can be any form of potential energy, right? Not that we need to see this, but rate of change of work. That's it's the same thing as this, essentially, same thing as this. This is just your calculus perspective, if you will. But we're not going to deal with that. But those two are equivalent. Much like velocity is, that is the same thing as this. We just have the algebra form at the bottom and the calculus form at the top. Conceptually the same.
Mr. Kelly, I don't know if it's me, but the board's image comes like half minute after you say something.
Repeat that.
The sharing image like comes delayed.
Hold on 1 second. All right. So that's power in a nutshell. Let's write up again. Work over delta T. So the units of power would be joules per second, which is equal to J over S. And we commonly call units of power, we take the units of power and call them watts after James Watt, 1800s, a lot of work, a lot of stuff he did with power. So 1 joule per second is 1 watt. W for short. 1 watt, W-A-T-T. Not 1 watt, 1 watt. You know, like your light bulbs have 60 W on there, the watts. Or were you making a joke? Yeah, I thought you. Geez Louise. All right, yeah, that's what it is. So let me just write up all of the power equations, their equivalencies. And we know that delta KE is also equal to force times delta X net force. So this is our third equivalence to W over T. Okay, because we know that this is what we got, what we derived the change in kinetic energy from the basic definition of work, which is force times displacement. And so if you take a look at delta X over delta T here, it becomes power can also be written as force times a constant velocity. So we have 3 forms depending on what you have. You have a force and a velocity, you can find power. It's the same thing as changing kinetic energy over time, changing potential energy over time, or just straight up work. Force times, average velocity or just velocity for short. And of course, all watts is the unit. Joule per second. When we take this out, it's only kilogram meters per second squared times meters per second. which is kilogram meters squared per second cubed. And a joule is a kilogram meter squared per second squared divided by another second, joule per second, which is watts. So this turns out to be our customary unit for watt, which is, let me just do a middleman over here, a kilogram meters squared per second squared. This is a joule because we have force times displacement. A force is mass times acceleration is a kilogram meter per second squared. That would be a unit of force times another meter, make it meter squared. That gives me a joule. Newtons times meters gives me a joule per second, which comes up to be kilogram meters per square second, which is the watt. This is all helpful just in case you get to a point and you have like this large abstract expression like I've been giving you. And you want to check the units to make sure that you have the units of acceleration and units of force or units of work. It's a good way to kind of check yourself on that. But yeah, so that's that would be the watt. So we have the concept of a kilowatt hour, and that's also it's a unit of energy as opposed to a unit of power. A kilowatt is 1,000 watts, and an hour is, you know, times H, or we can say 3,600 seconds is 1 hour. So that becomes a watt is a joule per second, multiplied by a second. And that comes out to be joules, or J. So a kilowatt hour is a unit of energy. And this is usually and depending on where you live, Glendale, Burbank, North Hollywood, where I'm at, you have a different rate of exacted by the electric companies. And based on how many kilowatt hours you've used in a month, that's going to be your electric bill, because they're actually tabulating how much energy you've used in a particular month, and they send the bill to your parents. So it's a kilowatt hour. Questions? So it's just the long short of power there. And also, not that this is used as widespread anymore, but unit of horsepower, you hear that sometimes with commercials, or car has such and such horsepower. It's 746 watts power is 1 horsepower. So if you have a problem that's in terms of horsepower, you can use this conversion to get how many watts there would be. 700 horsepower, how many watts? You know, so I know this my conversion. And then that's how many watts I'm gonna have. That's my common SI unit of power, is the watt. All right, so let's multiply that. We get 522,200 watts. Oh, 10 to the 5th, sorry. Okay, so that's a conversion, horsepower into watts. Okay, so I guess we can move on to the sample homework question. Or one of the homework problems. So looking at number 50, let me check something here. Okay, you guys turn there. We have a 200-gram particle is released from rest at point A along the horizontal diameter on the inside of a frictionless, nice, we're gonna deal with that, hemispherical bowl of radius r is 30 centimeters. In the figure, calculate the gravitational potential energy of the particle Earth system when the particle is at point A relative to point B, the kinetic energy at point B, the speed at point B, and its kinetic energy and potential energy when the particle is at C. So let's draw this figure. So A would be at the very top here. And so, and the C here, yeah, it's going to be 2/3 of the actual height. And so this will be, you know, of course, h equals 0 down at the bottom. And then at the very top, it's going to be the full height. Okay, so we have this. So the issue here from A to B, like we were saying last time, this path here is not important because what this path here dictates is distance. We're only interested in displacement, final minus initial. I'm starting at the top, I hit the bottom. Final minus initial displacement. Even though this looks like this, it's going to only travel through this displacement, h. So the path is not important. The shape of the path is not important. So let's get the gravitational potential energy of the particle Earth system when it is at A relative to point B. So when they say this is relative here is, you call this 0. We can define you can find this 0. Keeping things simple, conventionally, we go from a large value up in the air to nothing at the bottom. This is ground, 0, all that stuff, right? And so the bowl has a radius of r. So this radius can be subtended all the way up and around the bowl. So the radius of the bowl is also the height that from the perspective of top to bottom. So the radius serves as the height coming from top all the way down. So this another formal picture here, radius here. So that's the block is going to fall from top here to bottom there through this path. Who cares? Is top to bottom, final minus initial. okay? So therefore, as we've stipulated last time, we're going to be losing potential. It doesn't matter if you report it as positive or negative. Usually they'll say, what is the magnitude of it? If you give me a positive or negative, it's okay, not unless they, say signs are important. We're going to get the number. We know that the work done by gravity here, which is positive, is going to be equal to a loss in potential. So that's another story for later on. All they want you to do is find the potential energy at this point. We're not interested in this yet. But of course, we can use that when we need to. So that's the easy part, because when we try to find potential energy at a certain point, we'll just use the height. We're not interested in delta. So MGHA. So the mass will be 0.2, of course, gravity, and then the radius right up there was 0.3. And that gives me 0.588 joules of energy at A. No change, no nothing, it's static. Potential. The potential to convert to kinetic, the potential to move, the potential to take this energy and change it into another form, keeping the same amount, but changing the form. Questions? So remember, PE at A is not equal to delta PE, which will involve two points. Every time you see the delta, it's always 2 points. Going from something to something else.
But we can do that,
Starting
so,
point to an
right?
ending point. Whether it be delta
And
X
we
back
would,
to way day to change in entropy of the universe. The universe is here and now over there. What's the overall delta S, the entropy change? Final minus initial. Who can tell me what B is? What is the kinetic energy of the particle at point B? Someone I have not heard from, maybe you can chime in because you are eager.
is the potential energy for
I'm
A?
sorry?
Is the potential energy for A? It transforms to kinetic energy for B?
Yeah. And my volume was down, but could you tell me the number? What did you?
0.588.
Yeah, exactly. So we are exactly changing the potential energy at the top to potential energy at the top to kinetic energy, which is going to be 0.588. It's just a transformation. The amount doesn't change, the form changes. It goes from at rest, not moving, it has all of its energy as a function of potential, of position, transforms into kinetic energy, which is a function of speed. So at the bottom, it's moving. Even though at that level, H, the position is 0, H equals 0, the kinetic energy is maximized. You will hit the ground with maximum speed force in a very small amount of time. You don't have a parachute. So yeah, the ground is 0, you're not. Your speed is not 0. Okay, so yeah, we just transform it to same amount, 0.588. Now we can find the speed at point C by taking the kinetic energy equation, or point B, rather. And then we say 1/2 mv b squared. We're trying to find that. Any questions on that? I see, you know, they should see that by now, the formula for kinetic energy. So all we're doing is we're tracking the motion of this particle. We're looking at it in terms of its different energies that it has at different positions, the velocities. We can even do something, how much time did it take to fall? What is the acceleration? Acceleration due to gravity is the only thing that exists. We're closing it off from the environment, so there's no acceleration from friction or air resistance. Makes life easier when we close things off, at least in physics terms, not in society's terms, but it's another story for another day. So we have 0.588. That's what we got from part B. 1/2 mvb squared, okay. Multiply both sides by 2. Oh, darn thing. So yeah, so this guy's gonna be 0.2. Multiply, divide by 0.2. Square root. And who wants to tell me that answer? Let's work that out.
$2.42.
All right. Yeah. Woo. 2.42. Thank you, Sen. That is the speed at the bottom. Proof. You're going to have speed at the bottom, even though height is 0. Kinetic energy is changed. Our potential energy is changing kinetic. And now part B. What is the kinetic energy and the potential energy when the particle is at point C? The inference is that it's going to have both because it's in the air and it hasn't quite reached its maximum height again. So just to diagram that out, here is potential. Here is kinetic. Here it is both because it is in the air. Say here, 2/3, whatever. Try to get to the center. 2/3, it's in the air, but it hasn't quite lost all of its kinetic. So we have 2/3 of its energy is potential at this point. 1/3 is kinetic. It's still moving. The implicit reason why we know there's 2/3 kinetic energy because the height is 2/3. Potential energy is a function of this. So what's left? 1/3, not to the environment, not to heat. It's in kinetic. It's still moving. That's why it's still going to have both at this point, like we did with the ramp. You know, it's going to have both. It's going to have both when it's not at 0 or max height. In the middle or somewhere in between, both. Always. Okay. We can make life easy. We can start at A and go to C. Because remember, going back to chapter 2 or the beginning of physics here, that we can choose any reference point. This is my start and my finish. This is my start and my finish. Right here, if I wanted to, got to find something out over here in my finish. It's all about where you start, where you stop. Starting at maximum height, I'm ending at 2/3 of the maximum height. I have both energies because I have 2/3 of the original height and the other third is in kinetic. Okay, so let us press on. Kinetic energy and potential energy at C. So we are going to then convert the energy at A and put it into kinetic at C. And potential at C. Now, okay, so we can do that. That's the general, conservation of energy equation. We know this. We can calculate for this. We don't quite know it yet to use it explicitly. But once we do, we can then find the kinetic energy because that's the unknown. Mass still the same, still the block, gravity doesn't go anywhere, and the height changes. And we have 2/3 of 0.3 is something. Fractions. Okay, so we can put that in there. So 2 times 0.3 divided by 3 is 0.2 right here. 9.8. .39. 392. You guys get that? This is C. Potential energy at C. And there's that. All right, so we have A, we have C, the potential energy there. We can just solve for the unknown. And we should all check out. You should not get a negative number here. Still moving, Scott. So, kinetic energy, the bigger reason, it's not just algebra. The kinetic energy itself cannot be negative. Even if you have negative velocity, it's going to square. But the change in kinetic energy can be negative, especially when friction, well, presence of friction, slow things down from 5 meters per second to 2 meters per second. So 2 minus 5, you're going to have a negative change in kinetic. But kinetic energy is static. The object's moving at a constant. Kinetic energy cannot be negative. All right, so potential energy at A, 0.588 minus 0.196. And we can even use that to find the speed at C. Why don't we go ahead and do that as an exercise? Someone else chime in, Selena, I want you, everybody does it, you guys can talk back and forth, whatever, but Selena, I want you to give me the speed at C. I got the kinetic energy at C.
What did you want, Mr. Kelly?
I wanted this velocity at part C, point C.
Okay.
Yep. Okay, we're gonna verify that. Nicole, yep. Okay, so 2 different answers. Okay, let's see. So again, that was the bowl. Bowl works like the ramp and any other crazy path. For example, I commonly drive up to Berkeley, my alma mater, using the 5 freeway. Dude, crap. Okay, that's relatively straight path. But one time, I went up the coast. Doesn't matter. I still started and stopped at the same point. It just took more time because of distance. This is what it's all about in physics. Life easy. This was tough. That took like 10 hours. This takes 5. There's switchbacks. You're not going at a relatively constant speed. There's all kinds of issues. So it's all about the points. The path is irrelevant. You get it, Selena? Okay. Well, we're about to do the answer now. Okay, let's see if you get this. Okay, we got it here. Yeah. No problem, no problem. Okay, so kinetic energy at C, we got that already, right? 0.196 joules. And yeah, it's 1/2 mvc squared. All right, Selena, I know you got this already. You're already working on number 62. You're just a boss like that. Okay, 0.196 joules. So then, what's the mass again? So it's the same logic as last time. Square root BC. So this is 1.96, and then we take the square root of that. And we get 1.4. Yeah, so 1.4 meters per second. Just to go over it again. So we multiply both sides by 2, and that goes away. It should be mvc squared, or m mass is 0.2, and divide. And anybody questions on that? How did we get that? Issues? So that's energy, really. I mean, life's easier. It's all about the points. I identify my starting and ending points. What kind of energy is at those points? Solve for velocity, solve for height, solve for time. So yeah. Yeah, I said momentum is like the integral of force, and and it's also the derivative of energy. Those things become like really valuable on your college level. You can bounce back and forth between force to energy and momentum. especially with momentum and energy placed into the Schrodinger equation of quantum mechanics. They're so hand in glove, it's ridiculous. So that concept comes down the pipe, useful, the true usefulness of it. All right. So let's go on to our next slide here. Let's introduce the concept of momentum. Try to be as simple about it as possible. And don't worry, we're not going to abandon energy. We're going to do problems in that. Just introducing concept. We're going to continue after Thanksgiving, obviously. They work hand in hand, both conservation principles. Again, I'm going to be here after school today for office hours. Technically, chapter 9, linear momentum and collisions. Linear momentum and its conservation. So I'm just going to belay all of that so-called introduction they have there in section 1, because there's a lot of madness happening there. But let's have a conversation. We have a particle, and he's moving along. Constant velocity, nothing happening. By Newton's first law, we know, he's going to continue going along. The net force is equal to 0. There's no forces. That's going to cause that speed to change. So we know first principles, velocity, delta x over delta t. And that's, the whole kinematic stuff. We talked about things without the mass, without the causes of the motion. We just talked about the motion. So the motion in this case is going to just be velocity, change in position over time. And if I want to change my position, my velocity, it's going to be an acceleration. So this arrow is going to get longer and longer every second. But then by the time we get to, like, say, chapter 5 with forces, we introduce mass. Now this point particle is not just an arbitrary construct. It has value. This is a point. It's a ball rolling, car moving. Give it mass. So we now have this mass moving at this velocity. And when we couple them together, because they are together, this mass is moving with v. That is the concept notion of momentum. Momentum is mass times its constant speed. This was chapter 2, kinematics. And now we introduce mass times the same speed. That is momentum. That's it, the concept. And then we know that the units of mass are kilograms, units of velocity are meters per second. Therefore, the units of momentum are just a kilogram meter per second. It didn't have a nice little letter to that one because M is taken, for example. That is all. That's it. So someone asked, is that it? That's it. That's momentum. At least it moving along, constant momentum, if you will. Then we get to the change because life changes. Things, we have pesky forces, and that is it on the initial concept. Yes. Momentum. Is it a function of mass? Not necessarily, not as it's written, it's a function of velocity, but the mass with a velocity. Now, there's going to be that same mass that can change its velocity. And life changes, right? Because curiosity, or you've always been dealing with rates of change. That's just kind of like we live in a space-time continuum. We use time in everything. How much time is there in to change things if we must. Now, so the momentum concept here is really an offshoot of Newton's first law. It's a momentum is constant when the net force is equal to 0. Now, when we have acceleration, when the net force is not equal to 0, we change its momentum in time. So now, let's say we have a hockey puck comes in, and this mass is velocity here. It was moving at constant speed, and then that wasn't cool. So let's say we have a velocity here, then it gets longer and longer still. Okay, the velocity is changing. Hockey puck comes in, and outside force comes in to unbalance the system. It changes from net force equal to 0 to mass times acceleration. Now the velocity has it's taking greater values every second. It's speeding up. It's accelerating by the hockey puck, or baseball, or whatever agent comes in. So the momentum is changing per time. The momentum is changing per time because the velocity is changing per time, because the relationship here, momentum is a function of velocity. So when this guy changes, so do you, right? So velocity changes, so is momentum. So we have delta P over delta T equals mass delta V over delta T. The beauty of this, that this is an example of Newton's second law or an application of it, is because we know that this is mass times acceleration, which is equal to net force. Therefore, force is a change in momentum over time. Another way of saying force. Do you see that? Do you see how beautiful that is, that relationship? Questions? We change the momentum, Newton's second law, application of. So you can already see the relationship of force to momentum and even to energy. Like I said, that momentum is the derivative of energy, or kinetic energy more, because we have to have a speed. Potential can't do this. When we take the derivative of this, we multiply this by 2. 2 minus 1 is just 1. We get mv. Well, look at that. Trying to emphasize that. Energy per time, the derivative of it, the derivative, not work, but kinetic energy. So, because that would be a misnomer, because we know that E is the same as work, it's just, they have the same units, that gives you power. But I'll just, just to keep things simple here, changing energy per time is momentum. And the integral of momentum is force. Which is basically that here. We integrate this per time and chain rule. Yeah, I won't complicate that, but that's kind of relationship. We have a force relationship, but the thing to keep in mind, okay, that was just ranting and being tangential here, but momentum is mass times velocity. Cool, simple, and then when we change the momentum per time, we get a force. Let me explore this even further, okay? But do we all see this? Is this weird, confusing? We can make that jump from mass times velocity to change in velocity. Because anytime we change something, it's with respect to time. It's just like it's hand in hand. We change position. It's going to take time to do that. Change velocity is going to take time to do that. And as we change the velocity and the time it takes to do that, we're going to change the momentum because they're hand in hand. They're directly related. The momentum is related to velocity. It's like kinetic energy is. That's why the relationship is so seamless. So yeah, that's the momentum. And then now what I want to do is do something with that equation in the box that you guys are looking at there. I've changed momentum in time, I get a force. Allegedly, this is the first form of Newton's first law. Newton wrote his formula in terms of which comes out to be mass times acceleration, as we see here. Delta P over delta T is mass times delta V over delta T, which is acceleration. You got that? You know, no news is good news, but you know, I want to make sure that we can make the initial connections. All right, so let me just continue here. Constant momentum, or we just say momentum. I change my momentum. Okay, if I want to talk about delta P over delta T, let me bring down that other form. I just want to talk about delta P. I won't talk about force yet. This is force, okay? Delta P, M delta V over delta T times delta T. That should make sense. If regular momentum is M constant V, then delta P is M delta V. So I have this particle moving along. Its velocity is changing. It's going from an initial velocity to some final velocity. That's why I have my delta V here. Okay, so that's just showing that you could see hopefully you see this, the simplicity of that. So P is mv, then delta P is mass times delta V. Because wherever this goes, so does this. This doesn't change, constant. Change, change. Related. Still the same ball. So mass is same. Now, I want to introduce a concept called impulse. All impulse is the action of, say, a baseball bat on a baseball. So a baseball comes in, the bat hits the baseball, and it changes the speed. The impulse is the force of the bat in that small interval of time together. Just the contact. Some agent causing an object's speed to change provides an impulse. Baseball bat on baseball. hockey puck on, or hockey stick on hockey puck. You're playing kickball, your foot on the ball. The foot on the ball is the impulse. It provides the impulse. So you have delta P over delta T, which is that. Oops. This is force, which we've alluded to up top. Impulse is force per time. So I multiply both sides by delta T. This is my impulse equation. Not quite. I'm not quite sure the impulse from biology. If it had, I would assume it does not have the same form. The impulse from biology, does that use like nerves? Are you talking about nerve impulses? So it's same word, but different context, I think. Yikes. This is impulse, which is equal to a change of momentum. The baseball is going to change the momentum, or baseball bat is going to change the momentum of the baseball. Comes in at 95, it's leaving out of here at 137 miles an hour. Accelerates it in a small window or a large window. It depends. So this is commonly called the impulse momentum theorem, similar logic to work kinetic energy theorem. Impulse is a change of momentum, like work is a change of kinetic energy. See the parallels? And we've already seen a parallel that energy is related to momentum. The derivative of kinetic energy is the momentum. So there's a marriage happening there, energy and momentum.
Mr. K, should we put delta in front of force?
No, because what's happening is that, good question in the context of this. In reality, it is changing, the force is, but we either make life easier in basically algebra-based physics. We're going to make that force a constant force because the window of time normally, or a lot of the times, is a small window, so the rate of change of the force is zero, meaning that the force is just going to be a constant. So we just keep force as F. Okay, so we don't do a delta on that. Let me another point here before I do the next point. Yeah, so this impulse momentum theorem, similar to work kinetic energy theorem. So like as Sin asks, should we do a delta? So in reality, let me show you the reality first. So let's say the baseball comes in and the baseball batter, your Dodgers, just won a World Series, Mookie Betts. Okay, he initially makes contact with the baseball. So the force is going to be very small at first, and then through the middle part of the swing, the force is maximized. And then as the baseball leaves contact from the bat, the force starts to diminish. It starts to get smaller until it reaches nothing. So this is like mid swing. We have maximum force on the ball. This is ramping up here from initial contact to just when the ball leaves or stops making contact with the bat. Initial contact, lost contact. So in reality, the area under this would be the impulse. Because we saw, so impulse is change of momentum. So F delta T is, that's what I was gonna write too. So impulse is force times time, which is equal to M delta V. So impulse is the area of a force delta T, delta T is time, it's a time interval. It's the area of a force time graph. And in reality, that force is going to change, but we're gonna call it, I guess I started from 0. We're gonna call the force, I should technically have started like right here. For the most of our problems, we're gonna call this force an average force. And so that force is gonna be like, it's gonna look something like this. So we're gonna say on average, it's a constant value. It starts from 0, then mid swing, while the bat is in contact, from initial contact to final contact, same force. So that's what we're working with in our mostly algebra-based physics. So impulse is average force delta T, which is mass times delta V. Good question. So I think let's do a example problem. Regular impulse or regular momentum. What's going to happen here is that we're going to take this concept and we're going to derive the conservation of momentum. Very similar to conservation of energy. Close everything off from the environment. The only forces that exist is between 2 or more objects, like billiard balls on a pool table. They all have the forces in between. Any outside force, like from the felt on the pool table or air or anything, is closed, doesn't exist. I'll tell you, they have a hard time introducing stuff. We'll get to the number one's form in time, but let's see. Someone's mass is 5. This is actually beneath your pay grade here, but velocity. Oh boy, oh joy. What's the momentum?
15.
Yeah, so 15 kilogram meters per second. All right, that's too easy. All right. Other book. Let's see. Do an impulse problem. Again, we're not going to continue with impulse, like, leave power alone. We're going to come back to power. This is just introduction.
Mr. Kelly, so in this case, there is no impulse?
No, because the velocity doesn't change. Impulse always involves a change of velocity. So let's say the mass of a football in the old AP book. Nice examples. Okay, so we have this guy. So 0.5 kilograms is thrown toward the east with a speed 15 meters per second. So to the east is going to be positive. You know, a stationary receiver catches the ball and brings it to rest in 0.02 seconds. All right, so so find the impulse. Yeah, yeah, shoot. Okay. So why don't you do that right now? So find the impulse, and I'll give you a couple of minutes. What is the impulse delivered to the ball as it's caught? So the impulse by the receiver. So I'm gonna give you a picture here. So we have the receiver here. So next time we're gonna see that the impulse delivered by the ball is equal and opposite the impulse. So the impulse of ball on receiver is gonna be equal and opposite receiver on ball. Same magnitude, different direction. And the reason for it is because the time interval of the catch relative to the ball and the receiver is the same. Therefore, impulses are the equal and opposite, like force is equal and opposite, because it reduces to that. Yeah, values are here. And then the second question was, what's the force by the receiver on ball? So again, impulse, you have two options. Force times delta t. I don't know a force. I got a time, but shoot, is there another way? Yes, m delta v. So the screens are not lagging or anything. You guys can see this all right? All right. So let's see if we got the impulse here. So it's mass times delta V, and we got 0.5 times the velocity change. So it's going to be, final velocity is 0, as we saw up top, minus 15 because it's going towards the east. And that's 0.5 or half of 15, which is 7.5. And it's going to be negative 7.5 kilogram meters per second. But conventionally, the units of impulse are newtons times second. So impulse, you can use this. This is fine if you have that, because kilograms times meters per second, it's cool. The conventional ones are Newton seconds. So we can say this. And if you put because force times time, and force is kilogram meters per second squared. Multiply that by second. That comes out to be kilogram meters per second or Newton's seconds. So it's same. Questions on that? Is it seems clear? Because look, the ball's coming in. The ball impulse is going to be positive because he's going 15. He's starting from rest rather than 15 minus 0. So his is going to be positive, but the impulse of the receiver is equal and opposite. Negative. So the ball's impulse is 7.5 Newton seconds. The receiver is negative 7.5. So the net impulse, 0. Just like net force, 0. All the relationships starting to form, take shape, right? Because we're going to use this concept to derive our conservation of momentum. So start seeing these patterns form. All right, so last bit of questions. We got 2 minutes left. Did everybody get that? All right. I didn't get this impulse. What is impulse? I mean, wow, what did you just do the last 5 minutes, 15, whole time? Y'all good? Yes.